Okay, right. I'll start sharing my screen. Share screen, and I'll share the whole screen. Cool. Right. So thumbs up if you can see the screen.
Yep.
Yeah, I can see it.
Fab. All right, cool. So what I'm gonna do is I'm gonna run through, similar to the format before, I'll run through the presentation first. That'll give us an overview. And then if you want, we can step through the code. And if we want to spin off from there, we can try applying it to a different data set, or just run it from one of the example data sets. Either way, we'll learn something from it. So I'll click into presentation mode. Pop that down. Change it to there. Okay. I'll just hide everything because we know who's talking. Okay. Like we've got the concept for today. We're going to deal with is something called semantic segmentation, and the tool that we're going to manipulate the data with is UNet on Fast.ai. So it's a lot of the stuff, if you've seen previous Fast.ai ones, is going to seem fairly logical. It's just a little bit different in terms of what you're trying to achieve from the simple classification examples we've been doing up till now. So what I'm going to do is I'm going to go over what object detection is and explain the differences between that and segmentation. Then we'll look at what segmentation is used for. Then I'll give you a brief overview of what UNet is and how it works. And then I'll bust into how it works actually in practice in Fast.ai. I'm just going to check in case we're missing anyone. Yeah, just checking I haven't missed anyone else. I think it gives me notifications if anybody turns up. Okay, so that's basically what we're going to go through. Object detection, what segmentation is, how it differs, and then UNet and UNet Fast.ai. Okay, so object detection, you've probably seen this before. It's generally what it does is it takes an input image and then it has a selection of items that you would normally sort of classify on, and then it runs a classifier over the image, and it puts generally the output is a bounding box around what it thinks is an object, and it gives you the quality of the prediction. So it gives you what it thinks the confidence level is. So generally what will happen is you'll run the model, and it will, if you're using like region CNN or faster CNN or RCCN faster, what they'll do is they actually run the initial pass recurrently over the image, and then what it does is it uses a support vector machine to key confidence levels, and then it basically says which ones are worth classifying, and then that's where you get your output. YOLO is actually a wee bit smarter than that. It stands for you only look once, and it parses the entire image in one single pass, and it basically has a whole bunch of different boxes and does a prediction for each box. And then similar to the way that we were masking the predictions for the multi-label, what you do is you give it a confidence level, and everything above a certain confidence level it'll show. And then what you do is you just filter it for overlaps, because you don't want like 12 bounding boxes around a single car. So if they overlap, you generally remove all but the most confident one.
YOLO is a network, or it's just like how we put filters over convolution layer, like we see pixels and pixels.
Sorry, I didn't quite make out what the question was.
So I was asking, like, as you mentioned, like this RCNN and fast RCNN, and you say YOLO, and you're saying like YOLO decides like whether the object is in the image. So is it like some network in itself, some algorithm in itself, or is just like simply we are putting like how we put filters over the image in the convolution layer. So just check what pixels are there and then just figure out whether this filter is there on the image or not.
Well, YOLO is very similar to a normal convolutional neural network. The RCNNs, they work on a slightly different basis. If you want to dig into it a bit deeper, I've got a link here to a slide back that I did on object detection. I was really just wanting to at this stage show you what object detection looks like. So. We can maybe dive into object detection once we've gone through this, or we can have a little segue into it just now if you want.
Sorry, say again.
Oh, I was just saying we could potentially have a look at object detection in a bit more detail when we get to the end.
Go on with the presentation. I'll take a look later. That's fine.
Cool. I'll share the link to the slideshow.
Yeah, no worries.
So I'll move on to semantic segmentation now and how it's different. So it's basically, the big difference is it's much more fine-grained, and what it does is it applies a classifier to each pixel in the image. So it's not looking for objects within the image, it's trying to define which object each pixel is. So it's useful for things like describing the outline of an object. One of the areas this is really popular for is mapping. So if you take like a satellite image, you can then generate less dense and more useful information from it. So you can define like road structures, building structures, level of industrialization, detect things like airports and stuff like that. And when I was looking for examples, there's a lot of people using it to detect horses. Maybe they just like the look of them. So there's some really good segmentation data sets. Similar to most of the deep learning problems, you really need a fair number of images that have the contextual information already defined. This is actually quite a laborious task to do. There are some good tools to help you out, but what the human user effectively has to do is take the input image and then basically paint it with the different classifications that you want. So in this example, the CAMVID data set, they've went around and marked everything with a color based on whether it's a road, a tree, housing, cars, road markings, sky. So you can see how that would be quite an onerous task. The CAMVID one was one of the early ones, and it's a good one to work with because it's not too huge and you can get quite reasonable results from it. It's one of the local councils produced the data, and it's quite good for the UK because it's got the UK road markings on it, and it's overcast, which is your normal use case. The COCO data set is the.
Do they the segmentation? Do they color it frame by frame?
Yes,
on
each frame needs to be manually done. Some of the tools that they use, they automate it a little bit. So if it's a frame one after the other, they'll the mask will stay the same, and then you just adjust the bits that are needing changed.
The difference, yeah. It's labor-intensive task that if it's a long video or lots of frames in it.
Yeah, so this is the thing. It's you generally don't take you wouldn't probably do every frame because there wouldn't be a lot of meaningful information from that. You'd maybe take like 1 frame a second or something like that.
Yeah.
So COCO's that's Common Objects in Context, I think it stands for. That's another good one. That's got a genuinely large amount of images in it. 2.5 million of them, and they're labeled, sorry, 2.5 million labeled instances in 328K images. So you've got a nice big data set there to work with. Fast.ai's done a little subset of it though. It's a bit more manageable. So it's only got the chair, couch, TV, remote, and bays in it. So yeah, for us testing during the lockdown, that's probably all our cameras likely to see. And of course, Fast.ai has some data sets that you can use. Let's see what happens if I click that. You can see here it's got the CamVid data set, Pascal data set, and then it's got Coco. So it's got a good selection of them. Jump back to here. Go back into present. Where did present go? Oh, we'll just look at it like this. So other applications you can use segmentation for. One of the good examples in Kaggle is the iMaterialist fashion dataset. And what that's doing is it's taking fashion photographs and trying to define what type of garment is. So you can see this dapper fellow with his fancy little shirt and jacket, and you can see there that somebody's produced a nicely segmented image to even call out like its watch. So you can see here the output that I got from training Fast.ai. I think it was, I'm trying to remember what I used. I think it was, actually, I think it was exactly the same model as I'm about to show you. I think it was UNet for this as well. You can see the values on the left there, the ground truth and the predictions. And other than the bottom image, it's done really, really quite well. So you can see, unfortunately for that lady, it's not done a great job at identifying her shorts, but the clearer images of the pants and the t-shirt is done almost pixel perfect representation of what the ground truth was. You remember this is just a single fit one cycle, so only ran once. It did take 50 minutes though. Okay, so what's UNet? So UNet was originally used for medical imaging. So that's things like if you've got a slide or a mammary photograph, and what they're doing is they're trying to identify things like cysts and cancerous tissue and things like that. So what they were doing was highlighting the areas that the technicians should pay most attention to. But what they actually found is that this model was applicable to almost all segmentation problems. You can see here what the original UNet was, and it's really quite small. It didn't have an awful lot of complicated steps in it. You can see here it's doing 3x3 convolutions with ReLU to do the nonlinearity, and some max pooling and some upconf 2x2. So none of this is particularly complicated stuff, but the bit of genius to it is the idea of taking your input file, processing it the same way as you would do to produce like a classification, skipping the classification part of the network, and then do the reverse, almost mirror on the right hand side of it. And what that does is it then goes through the process of upscaling. So what really, really benefits us is that we've already got some great classifiers that can do the left hand side of it. So when we're training, we only really need to figure out the right hand side of it. And for doing the upsampling side, or what they call the encoder and decoder parts of the network. So if you see this side, this will look the left-hand side will look very similar to what ResNet would look like for doing image classification. So when Fast.ai to do segmentation, you need a function to define your mask. So that's generally going to be using an input file. So you create a small lambda function and create a new mask object using the open mask, which you pass then the function that you've created. like everything in Fast.ai, they've got some nice ways to visualize. So if you do mask.show, it'll give you a view of what the mask looks like. Then you use that mask in your data bunch constructor. You can see here that when we run show batch, it's even smart enough to overlay the original image with the mask, so you can see what parts of the original image are getting masked. Are getting picked out as specific subtypes. So here you can see that the trees have all been masked in green. The sidewalks are purple. The people are this sort of darker purple, and the buildings are this orange. So you can see, again, very, very little of this is going to be new. You've got the label from function where you pass your function in, and your normalization is exactly the same because you'll be using ResNet. You're going to be using the ImageNet stats again. Again, you don't think too much about it. You can take the defaults, but things like transform Y being true allows it to mirror the images. So yeah, none of this should be overly complicated. And then you construct your learner. And as you can see, you're using models.resnet 34 again. Now that might, I mean, I've got to admit this, when I first saw it, it struck me as really odd. ResNet is not a unit. Unit's a completely different thing. But Fast.ai is smarter than me. And the same way that when we do our transfer learning, if you remember, we'll take the rest of the smartly trained network, we break off the last fully connected layer and the softmax part of it that does the classification, and we replace those final two really simple layers with our own versions of them to get our own classifications. And we use all that juicy smart intelligence to apply it to our specific problem. Now, when Fast.ai looks at UNet, what it does is it does that exact same step. It chucks away the final fully connected layer and softmax, and then it mirrors it, so completely gives you the complete inverse of it, and generates the right-hand side of it, I think, with randomized weights and biases. So when you do your transfer learning and you start your training, this is where it varies a little bit from before. When we were doing the training before, what it would do is it would train the final layers when you were frozen, and then when you unfroze, it would train the already allocated ones that you've taken from the original model. In this one, when you have frozen and unfrozen, what happens when you're frozen, the entirety of the original ResNet model is maintained. And the only thing that's trained is the newly created layers on the right-hand side. So the encoder stays exactly the same, and only the decoder part starts getting trained. When you turn off the frozen, what happens is then it allows it to train the entire network. So again, what you would do is you get a pretty good result, and then only when you're doing fine tuning would you allow it to modify the input encoder side. And again, this is one of the things I love about Fast.ai. All of this stuff is done automatically. Awesome. Okay, tips and tricks. So batch sizes need to be small, as effectively you're running a classifier on every single pixel. That's using an awful lot of memory. The concept of progressive upscaling is very efficient on this. That's where you train on smaller image sizes and then you learn onto the higher resolution. If you scale or transform your images, you also need to remember to scale your masks. This is one of the things that came up in the MOOC. Some cases switching to mixed precision, so turning on FP16, can actually help with both accuracy and memory consumption. And according to Gilbert, this is actually the reason why I'm calling this out, is I couldn't actually find any documentation to support the things, the encoder being frozen, and it was only actually Gilbert Danner's blog that gave me the information about how the decoder side trains. I would take that a little bit with a pinch of salt. This is a nice little tool project. If you remember what I was saying, how it's kind of difficult to paint the images. And what this one's doing is it's doing a bit of quite smart boundary and edge detection, and it allows you to create your data sets quite easily. There's this little animated GIF is showing you how a end user would do it. So you can see how the first pass is fairly accurately defining the road and the forest. And then what happens is once it does the original first pass, you realize these little sections haven't been colored in correctly. So roughly roughly selects them and then runs the process again, and it gets you a pretty well masked image to work in your data set, which is kind of cool. So bump back to here. Trying to think if there's anything else. Yeah, if you want to get this done professionally, this is the link to course.fast.ai, and about 30 minutes into lesson 3 is where Jeremy covers all this. So that's it from the boring presentation. Have a look at it actually working. Or actually, what I'll do is I'll bounce to questions for a bit, and then we can decide what we want to do. Can't believe there's no questions after all that.
Okay, I was quite surprised with the tool though, the pixel annotation tool. Like, I'll be surprised if like it works for complicated things because it has just forest and road. But what if they're like, if we are annotating dogs and humans and cars and trees and houses and street lights, then how good is it doing that?
It's probably good. I'm definitely going to download it and have a proper play with it. But yeah, it does seem to be working for, like, I think it's basically working on edge detection. So for these this classic image, it's done fairly well. We don't know exactly how much work went into doing that though.
Yeah.
Does it do the thing on images, or is it on video as well?
Well, because you the data, the input to this won't be video. What you would do is you would take specific frames out of a similar to the way you do most video classification. You don't do video classification. You take an image. So if you can do, say, 7 inferences a second, you would take 7 images per second. You wouldn't take the full 24.
No, my question was like, if you've got a whole video and everything, you just put that video in it, or you just take the frames out of the video first and then put those frames or those images in this and then run it?
What you would do is you would grab the you would grab the
frames
images
and everything,
and then process the images,
and then process the images. Okay, I was wondering if you could put an image, the whole video in it, and then make segments of the frame, and then you do it on that.
As I said at the beginning, the process for doing this is fairly laborious. That's why
it's much better than the manual pixeling, doing it manually.
Using the existing data sets is definitely the way forward, unless you've got a very specific task. And most of the time, what people are doing is they're identifying things or classes of problems that people have already solved. So using something that's been trained to detect ships at sea, or using ones that have been detecting like Amazonian deforestation, they're ones that have been trained to deal with satellite and mapping data. So they'll probably be the good ones for you to transfer learn off of. And then there's a lot of self-driving car work that's been done. So those data sets are really good for building things like robots or people detectors or any of those sort of tasks.
Yeah, yeah.
So, okay, well, what do you guys want to do? We could either just dive through the notebook. I can maybe pull it onto Colab or something and try and run it. The difficulty with doing this is you can see if we scroll down to the first epoch of training. Yeah, it's one of these ones where you're better off kicking it off and then coming back.
Go for a lunch break or something like that.
Yeah,
come back.
This was with a GPU. And part of the problem is if you go back, if we scroll back, you can see here batch size. We're only talking about processing 8 or 4 images at a time. Whereas when we were processing like the food data sets, yeah, I mean, you could throw like 200 of them in at a time.
True.
So it always, I mean, that's the thing as well, is it scales based on the size of input image. You're generally
it might be worth asking Vishal. He's been using, I think, Colab Pro, he said. So might be if you
I
got
don't think it
Colab
will
Pro.
help. Even like if it's Colab Pro, the numbers he is giving, I don't think it will make a big difference because um, uh, when you go from K8 to P100 graphic card, you see some jump, but it's still not that big.
Yeah, when I was running this, I was running it on a Volta 100, so it was the fastest
even better
GPU at the
than
time.
Yeah, with Colab Pro. So I don't think, but I think it's the same RAM though for P100 and V100. The 16 GB is the flops which are more in V100, if I'm not wrong.
Yeah, I think the P100 is meant to be it's like a cheaper version than the V100.
I think it was just because it was designed in 2016. V100 came later, so I think that's the only chance. So they improved on the number of threads they can compute at the same time.
All right.
So yeah, I don't think, as you said, then we can go through the code then. Either we can go through the notebook if you have the outputs in the notebook, so we can just scroll through your outputs and see what's happening in each cell.
Yeah, we do.
I think that would be better. Yeah.
Yeah. Okay, cool. Right. Well, what I did is with everything, I start with the original source material. So I took the example that Jeremy had produced for doing the CamVid data processing. That's actually quite nice because it runs fairly quickly because it's got a nice small data set. What I was doing is applying it to the iMaterials fashion data set, which has got both, it's I think 30,000 images, and so it's a significantly larger data set. So we've got our the only thing that I messed around with here, I think, is that I pulled in progress bar. That was to allow me to, I don't actually think I ended up using it, but that was to allow me to show the progress of some of the longer things like doing the unzipping. So we create our path. Here I've downloaded the iMaterials data set, and it shows you the files that are given to you. So you've got a test and a train data set, you've got your labels folder, sample submission. So if you've seen Kaggle once before, this all of this will seem fairly reasonable. Usually the sample submission CSV showing you what format they want you to present your results in. You're testing your train data set. Usually in Kaggle, the train data set is the one that you're to use for your training and your validation. The test data set is usually the data set that they are wanting you to run your process on to produce your sample submission. The test data set will not come with labels. So what we're doing is we create a folder for the mask images, and we create a folder for the models. And then we take the input data, and we know that we've got 27 apparel items because the data tells us that in our labels JSON file. So you can see here that what it's doing is it's identifying things like shirts, blouses, tops, t-shirts, ruffles, and sequins. It's quite good fun. And then you need your function. So this is the function that we're using to define what each of the encoded pixels is in our train.csv file, and it basically creates the image mask. This will get fairly complicated. If you're running I've got a bit. This is the way I would do it. If you're running a Kaggle competition, have a look and see if anybody's already created an example notebook. Quite often the organization that's running it will put a basic, not competitive notebook up, and that will have the things like the processing of the data input in there for you, because it's, to be honest, fairly boring stuff to do, and I'd rather be doing the machine learning bit of it than defining how they've chosen to build their data for you to process, if that makes any sense. So yeah, I have to admit I stole this little chunk of code off of somebody else's, and it was nice because I don't know if I would have been able to have written that myself. So once you've done it though, definitely rattle out and do an image.show to make sure that your data is coming through and getting processed well. You can see this is showing you a single image, and it's a picture of a nice person that what looks like a opera or something like that. Looks pretty good. And then you should do the same for your image mask to make sure that that's coming in quite nicely. So I generally like to do it for the exact same image, because then you can sort of see if the mask is offset, and you can see that this does look like the mask and the image tie up. It looks like the same thing, and it looks like it's not mirrored or flipped or anything like that. That's good. And then you create a 3-channel PMG, and then open up your masks. So you can see here that again, I'm just checking at each stage. This is something I would really encourage you to do. You don't really want to start training your model and realize that it's all going garbage and not then assume that there's something wrong with the way you're doing your training if you haven't actually set up the inputs correctly. So take good use of the visualization functions, and at each step check that what you're doing is right. So next bit is to produce the masks. So you generate sorry. Yeah, you only this actually takes quite a while, and that's why the progress bar was in. I only did this the one time, and what it does is because it's creating what you're doing is you're creating a PNG file that maps the information in the CSV. So when you've got those two, so what you'll have is effectively an input image and then another input image which contains the masking data. So when you're doing this the first time, you'll need to run this process to generate those images. Once you've generated those images, you don't have to do it the second time. Just leave them sitting persisted on your hard drive. You can see here what I'm doing is I'm just doing the usual data exploration, trying to see what the file names are, trying to see that I've got equivalent labels. And these are the PNGs that we created during the mask production part. And then we define our lambda function, and because we've created the this simplifies things quite a lot, because we've created the output PNGs. We can make our lambda function just to tell it to look up the exact same file name, but with _p at the end of it. So you can show your input image, and then you can show your equivalent mask. You can see it's the same thing. It all looks fine. We can define all our codes. Then we define which batch size we're using. So you need a bit of wiggle room to do 8 of these at one time. And you can see here what we've done is we've split the model size and we've halved it. So we're training on a half-sized image. See, it's gone down to 112 by 112 pixels. And we've got a small batch size. When this one ran, oh, actually, I must have been running this on a K80 because I got batch size 4. You can see from the output. So you do your source and your data, same thing as before. I showed you, it's you build your data bunch, you normalize it, your source. Again, we pass it the function, because this is how we're labeling it. And then we show a batch. And the good thing about having a show batch here is that you can see the images have been overlaid by their masks, and it does that all without any effort. Sorry, my boys need a wee hug. There we go. Okay, you're hugged. Bye. I'll try. And I've shown a second batch just to see if I don't know. I actually know why I did the second show batch. Yeah. Oh, sorry. I was checking the validation data set. Also looked good. As you can see, that's the difference there. I'm doing a show batch of the training data, and then I've said that I want to see the validation data set the second time. This one needed a different accuracy matrix. Generally the competition will tell you what it's going to. It's going to tell you what they're assessing you on, and generally they'll also tell you how to write the mask. In this case, I think what it was doing, yeah, it was excluding the background pixels. So you see these unallocated pixels here in the background. What they were wanting you to do is report your accuracy on the basis of only classifying the clothing pieces. So they only wanted the apparel to be correctly allocated. Everything else was meant to be allocated to 0. And this is one thing to remember as well, is that your accuracy that you create, your accuracy metrics, they don't actually do anything different to the training. They're just ways of reporting information back to you. So I've defined weight decays here. Don't know why I've done that one. 1 to the e minus 2. I think that's actually, I'm not 100% sure. I think that actually might be the default. I don't know why I've done that.
It's the default.
Yeah, I was maybe just confirming the default. And then this is I know it all gets really complicated here, but rather than creating a learner, you're creating a unit underscore learner. You pass it the model that you want to base it on. You pass your weight decay, and you pass it the model directory. Run LR find, plot the output. You can see here it's got a nice steep trajectory. So we would guess we'd probably want to do something about, I would have said, actually, I would have probably gone a bit before 1 to the e to the minus 3, because that is here. I wonder if maybe I didn't know how to read these graphs when I did this, because that's not actually a particularly good learning rate. You'd probably
I was
want
doing something between, like, it could be 4 ES
yeah.
of -5.
Yeah, if I think I did this again,
-5 -4.
I would have probably gone
-4.5, yeah, something like 4 -4 would be good.
Yeah, that would have been a good starting point up at the top of the graph and let it slide down. I think I did 1 to the e to -3 because I didn't know any better.
Yeah, and also when you do like learn.render.plot, so in that learn.render.plot, if you like suggestion equals to true, then it also gives you the value which you should put.
Oh.
Yeah, so
Yeah, didn't have that when I did this.
yeah, so you can put like suggestion equals to true, so it gives you a red dot in the graph which it thinks you should use, but it's not very accurate, but it's still like gives you a good indication.
Ah, that's cool. I'll definitely try that. So it's learn.plot and dot suggestion. Okay, cool. And then you run your training. You can save and load it just like normal, and you've got show results. So this one, what it does is it shows you your ground truth versus your predictions, taking out your validation set, which is nice. It's, as I say, I thought it did a fairly decent job, but because I'd already burned about an hour on training, and I'd burned quite a bit of other time getting the model to actually train. That's where I just gave up and stopped. So I don't know. iMaterialist is still that's still a competition you can submit results to. I wonder, do we want to maybe take my crappy first attempt from over a year ago, and for the week we could try and improve it and see if we can move up the rankings and put in some better accuracy than 0.86. I still thought, to be honest, 0.86 accuracy after a single epoch was fairly good. But shall I kick off a VM and we'll have a go at it? Or?
Yeah.
Or some other metrics as well test you on?
Sorry?
So I was asking, like, is just the accuracy which you are being tested on, or some other metrics as well?
Yeah, the generally what well, it gives you your training, your validation loss, but then what we're doing here is we're showing the accuracy that the competition is going to be gauging us on. So,
All right.
remember this, the competition only cares about you correctly allocating the.
What was the accuracy for the first 10? What was their accuracy at?
Oh, I don't know.
It would give us a ballpark figure how far you are from the top leaders.
Yeah, let's go. Kaggle. Leaderboard. I wonder if I've got my accuracy correct. The score is 0.89 was definitely better than 0.32.
I don't think it's accuracy.
It's something else. It might not
If you
be.
go in overview, you can see what score they
See
are.
what they're checking.
Yeah, intersection over union, object segmentation with classification.
I think they give a formula or something that's you put that at the end of your code, and that's how you get this number instead of just the accuracy or something. It should be in their overview.
Mm-hmm. It's done fine grained classification.
Yeah, just go on evaluation, I guess.
Yeah, and the evaluation part.
In order to
As
produce,
software.
I should try and length encoding and pixel value. All right, okay. Yeah, and this is part of the reason why the if you remember, the code to produce the masks was quite complicated. It's because they've used this compression process on the training data as well. It's just annoying. I've got to admit, I'd have rather just downloaded more data. Yeah, so those are 7. Yeah, it's closed a year ago. So the good thing about these is the closed ones is that you can see lots of public notebooks. You can probably
It's
find
better
some.
for learning, yeah.
Yeah, there's probably some good. Yeah, so there's a Fast.ai factory report using mask images. Bet you that one doesn't look too different to the one I did. I like the way his shopping bag's also categorized. Oh no, it's his laptop case.
It's laptop case, yeah.
Oof.
He's got a lot of data time on it.
Yeah. Let's see what they did. Oh, mind you, he's getting, if you look at his accuracy fashion.
Accuracy, yeah.
Yeah, so he's getting
nearly the
roughly
same as
60.
yours.
Much quicker, though. I think probably what he's done is he's broken the data up and he's not processing the.
He's put the learning rate at -4. Probably if you put your learning rate at -4 or something, your accuracy might jump without any changes, if I'm not wrong.
So PCT start is 0.9, so it's actually allowing. It doesn't make sense. Why it's 0.9? Because it's saying like for 10 epochs, for the first 9 epoch, you should increase the value of so like how when we optimize this this graph first goes up, then it goes down. They're saying like just go up for 90% of the time and then just jump down to 10. I've never seen this before. Usually it's once you have trained on like 1, -4, -3 for like 3 or 4 epochs, people usually try to get rid of it. So it's default is 0.3, but people just go 0.2, 0.1, or sometimes put 0, so that I don't want this to go up again. Otherwise, it will jump here and there.
Yeah, when you see the normal graphs, it sort of ramps up, and then about a third to half of the way through, then it starts annealing back down.
Because 0.3 by default, the PCT start value is 0.3. So for first 30% of the training, it goes up, and for rest 70% it goes down. But it's saying like just go up for 90% of the time, and last 10% go down.
Yeah, that's a strange. Yeah, I wonder why they have played with that. There'll be a reason for it.
Yeah, should be something to try. I've never seen this before.
The epoch, the rate he got through his epochs was a lot quicker as well. 18 minutes an epoch. I bet you this is me getting caught using standard persistent disk again. I bet he was doing it on SSD. But you can see the output he's got isn't too different. In fact, admittedly, these are probably slightly more complicated ones than the examples I was showing. But it's not doing very well at allocating the skirt. It's made that like I think it's making the top a blouse. It's done well on that dress, but not so well on this dress. It's interesting. Okay, well, do we want to kick it off and try running it? And we'll maybe make those corrections, and then I can leave it running, and we can see what the output is tomorrow.
Sure.
Cool. Okay, I'll go on to. Won't do it on Kaggle. I'll do it on.
Also, one thing I noticed, like there was no augmentation. Can't we augment data in some way which can help us?
Yeah, well, this is the thing I was pointing out though, is that if you augment the data on one of these kind of challenges, you have to augment your mask as well. So anything you do to your image will need to be done to the mask. So, let's see. I think it's. Oh, I hate these kind of outputs. Let's see what he's done. Where's his data constructor? Because I think that's maybe why they're not keen on doing too much of the data augmentation. Is that if you think of, if you're down and upscaling things, distorting the image like you would normally do, I'm not sure if that would work well on your mask image. You could maybe do things like scaling it, but I'd be surprised. Because like if you
Like what type
slightly
of data
color
is the
shifting it.
mask image? Like it's pixel values, right? So if we are scale, because no, it's right, because when we augment, it's done randomly, so we can't actually track how it's augmented.
Yeah, I'm pretty sure that's probably why there's very little augmentation getting done.
I think still can be done, because we can get the output from Fast.ai, like what kind of augmentation it is doing on images, and what kind of augmentation was done on what images. Because when we do like show batch, we get those augmented images back, right, and with the same numbers. So if we know the image and we know the mask, I think we can transform the mask as well according to the augmentation done on the image, and then use that. So we'll have more data to play with.
Yeah, I think you would be able to, but as we're seeing here, it doesn't look like he's doing any default transforms.
Yeah, it's the default. He's using get transforms, so which are like default values. He hasn't done any transformation. He is doing transform, but like default values. He hasn't played any with the, like, he hasn't put any transformation from his own side.
Yeah. And yeah, so that's the only constraint he's put on it is the transform Y. Okay, right. I'm trying to think. Well, actually, well, should we just do it in Kaggle? I've got my 30 hours of GPU back again. I'm just thinking, if we do it, if we were doing it on, we need to recreate those masks, and the process of doing that takes about 30 to 40 minutes. Yeah, I think if we're gonna actually have a go of this, it would have been probably better to prep the data and things like that. But when I was asking it on
like, we can
Slack,
go to details and see what if someone has any idea, you just write that and comment it out, and you can try it later.
Yeah, sure, that would work.
Yeah.
So, I'll kick it off and see if it runs. Yeah, so accelerate my GPU. So we'll just skip through all the boring stuff at the beginning, all the hygiene stuff. So I think, yeah, I've got a sneaking suspicion the way that he managed to do this so quickly is he only took 5,000 images. If we scroll up here, yeah, it's just the 5,000 images, which is probably enough to get you going. But that'll be why his epochs were so much quicker.
What's the total number of images?
I'm trying to remember. Let's go back to amateur list. Jump to the data. We should be able to just see it from the data. Yeah, so
that's a lot of images.
Yeah, it was 48,000 images. So that's why my epochs were running slow, and that's also why the process of doing the extraction and creating of the masks took so bloody long.
It took you 51 minutes, if I'm not wrong.
Yeah, 51 minutes
For
for an
one,
epoch.
and he did 9 or 10 epochs. So what do you think is better, doing taking a smaller number of images and doing lots of epochs, or doing the 1 or 2 images, or one or two epochs on the whole data set?
Yeah. Well, I think given that they're doing the transformation, and what Jeremy keeps saying, because they implement dropout and weight decay, your
Mm.
your risk of overfitting is fairly low, especially overdoing something like 12 epochs. You really aren't going to get much overfitting, and it'll stay fairly generalized. So I suppose that's probably why that person's made I think the advantage of having the larger data set is that you probably would generalize more, and
Yeah,
I mean, you would de-risk overfitting by having a much larger data set.
you wouldn't need to augment to anything or else. So the masks and everything, you don't need to change them on the original data set. If you just take the whole thing.
Yeah, especially if you're only running one epoch.
Yeah.
You want to let the model see the data once.
Yeah. I think that's why his images, if you looked at his images, some of the dresses were fine, but the others were not fine. I mean, they were not properly segmenting them. I think because he's got a smaller number of images, that's why. And
So
the one
maybe
you
his
ran, it was on the full data set. That's why yours images were better, I think.
Yeah, and I think that's the thing, is that his one, unfortunately, there might not have been any big long ball gowns in the data set, so it would find it more confusing. Whereas, because I've got the much larger distribution of
Yeah.
data, it pretty much anything that's in the validation set you would expect to be in the data set that's in the test set. There'll be an instance similar to it, because otherwise you're training for the wrong problem.
Yeah.
And this is maybe another fault in the approach that this guy's used, is that he's just taken the first 5,000 images.
Yeah. Yeah.
He's not I don't think he took a random
He should have
5,000.
taken a random one. But even if you take a random one and you've got 48,000 images and you just take a set of 5,000, it's not going to be a proper general uh, learning.
Yeah, you do have to worry about it though. Is you've got to remember, a lot of these data sets get produced using sort of human processes, and it might have been a case that they took the J.C. Penney catalog photographs as their first 5,000.
Yeah.
So although across the board it'll have Asian fashions, ball gown weekly images later on, the first 5,000 might all be J.C. Penney stuff, or it might be all Marks and Spencer stuff.
Yeah.
And your model gets really good at identifying those images, just not so good at the rest of them.
Images, yeah. I think it's a matter of managing your time. If you've got a huge data set, if you want to take the whole thing, or it just occurred to me, what if you, I don't know if it's possible, if you've got 48,000 images, if you just split them in half and do an epoch on one, and then train another the same thing on the second images, and see if there is any difference in that.
Well, one of the approaches I quite like is cross-validation. So what that's doing is it's it takes your validation set and it rotates it out. I think, to be honest, I don't think this is going to be much fun for us to watch. We're only 15% the way through generating masks.
Even with even with the 5,000, yeah.
And as you can see, it's these anemic machines they give us with 2 virtual CPUs sitting burning CPU time. So again, one of the things I always suggest is, if you're doing something like that, turn your GPU off. But because of the stupid way Kaggle works, you can't do that, because if you need your GPU later on, you need to have it on for the session
at the start. Yeah.
I guess what you could do, if you were repeating this project in Kaggle, what I would suggest you would do is generate your mask images, then download them and build a new data set, and then use that using the add data. And what you can do is you can generate that, you can use that as an additional data set that you can input into your VM. That way, that'll be one of the ways of persisting it. Even if it's a case you need to download the data onto your own machine and generate the masks, and then upload them to Kaggle, because you don't want to be burning significant amounts of GPU time, given you've only got a 30-hour limit, whether your GPU is just not getting utilized. I guess that's you start to have to think quite sensibly about conserving resources. Oh, all right. Well, this has done an hour. Should we call it a day just now? And
Yeah.
what we'll do is I'll run this on a. I'll generate the masks on a and build it as a Kaggle data set, and then we can try we can try playing around with the actual models and the training, rather than watch it processing and generating a bunch of PNGs.
Yeah.
Sure. Also, I looked at the data size. I think I'll be able to run it in my Colab Pro. The size of the data is just under what I can run. It's like 21 GB. So the earlier one which I had was like 25 GB, and that was zip. So, but this one doesn't look like zip. So 21 GB. I think I can play with this during this week as well.
Yeah, that'd be cool.
I would be interested if Vishal, you told us how much time and everything it took into comparison, because I was also looking to get a.
I don't think it will take much different, because on Kaggle we get the same kind of GPUs. I think we get, if I'm not wrong, P100s or Tesla, one of those. So time will be kind of same. The GPUs are same both on Kaggle and.
Wasn't Colab Pro supposed to be optimized? I mean, they gave you the best of all resources and.
It does, but the best is still quite low.
Still not good enough. Yeah.
In general, you get K80s, but if you get Colab Pro, then you get P100s. So there is a significant difference, because K80 is like 8 GB RAM. You go from 8 GB to 16 GB, like double of it. The session is from 12 hours to 24 hours, and also your RAM is from 12 GB to 24 GB. So everything is doubled, but still, it's
you can get better.
What Kaggle gives by default is quite
yeah. I think it's Colab Pro is for people who got larger data sets. If what you're telling me is right, then
no, it's for everyone.
You get more resources, but not fast speed.
Yeah. But there's a limit to the when you get the VM. There's like a space limit, so you only get like 70 to 80 GB of space on your VM. So you can only utilize it. You can't. It's not like a AWS or GCS where you can add more storage. So you have a limitation with this, because it's again from a pool which they are giving you, but you're giving they're giving you on priority. That's it. Apart from it, there's no difference.
I think for $10 that's a good deal.
Yeah, it is. That's why I took it, because there's no limit like 30 hours like on Kaggle. That after 30 hours it will go off. I can just keep on running for the whole week without. And $10
isn't there a limit on how long you can run it? Because
there's a session.
I think Colab has gotten 8 hours.
But I think you can save your pickle files or PTH files and then start the session again and continue where you left. So it's not a problem.
And you have to access it via VPN then.
Because it's kind of illegal. So because it's only available in state. It's not available in UK. So you can use it for that. And someone has to give a US card details.
Okay.
Cool. All right. Well, I'll stop sharing so we can see all our faces again, and then I'm going to stop recording.